Hello, this is Math 2115 coming to you from the College of DuPage for the fall of 2020, and the title of this lecture is Arguments in Rules of Inference. By way of introduction, I'm going to talk a little bit about bugs because many of you are going to spend much time debugging programs. The first quote is from Thomas Edison. It's been just so in all my inventions. The first step is an intuition and comes with a burst. Then difficulties arise. This thing gives out, and it is then that bugs, as such little faults and difficulties are called, show themselves, and months of intense watching, study, and labor are requisite before commercial success or failure is certainly achieved. This will have a lot of meaning when you think about testing software. But there were no computers at the time that Edison said this, but that was not true for an outstanding woman scientist and engineer and officer, Rear Admiral, in fact, in the Navy, Grace Murray Hopper. Grace had a PhD from Yale in mathematics and served the country nobly. You don't become a Rear Admiral easily. In 1946, when she was released from active duty, she joined the Harvard faculty at the Computation Laboratory, where she continued to work on some of the earlier computers called Marks. Operators traced an error in a Mark II to a moth trapped in a relay and coining the term bug. The bug was carefully removed and taped into the logbook, and you can see a picture of that page here. Stemming from that first bug, today we call errors or glitches in a program a bug, and Grace Murray Hopper was the first person to call it that. Let's look at now an argument. The bug is either in Module 17 or in Module 81. The bug is a numerical error. Module 81 has no numerical errors. Assuming these statements are true, then you have to conclude that the bug is in Module 17. The process of drawing a conclusion from a sequence of propositions is called deductive reasoning. The given propositions are called hypothesis or premises, and the proposition that follows from the hypothesis is called the conclusion. A deductive argument consists of a hypothesis together with a conclusion. Many proofs in mathematics and computer science are deductive arguments. Any argument has the form if and then, and it's if P1 and P2 and P3 and ... Thank goodness for ... and P sub n, then Q follows. This is like an if-then statement that we've studied. Arguments are said to be valid if the conclusion follows from the hypothesis. That is, if P1 and P2 and all the way through to Pn are true, then Q must also be true. This discussion motivates the following definition. An argument is a sequence of propositions, often written this way, P1 through Pn, above the line. So this is the if part, and then it is therefore Q below the line. Or sometimes it's written this way. That symbol means therefore. So the propositions, P1 through Pn, are called the hypothesis or premises, and the proposition Q is called the conclusion. The argument is valid if all of these are true, that is, the conjunction of them are true, then Q must also be true. Otherwise, the argument is invalid, or sometimes called a fallacy. In a valid argument, we sometimes say the conclusion follows from the hypothesis. Notice that we are not going to say that the conclusion is true. We are only saying that if you grant the hypotheses, you assume that they're true, you must also grant the conclusion as being true. An argument is valid because of its form, not because of its content. Each step of an extended argument involves drawing intermediate conclusions. For the argument to be valid as a whole, each step of the argument must result in a valid intermediate conclusion. Rules of inference, brief, valid arguments, are used within a larger argument. We're now going to look at some of these rules of inference that are known to be true, and we'll talk about why they are true. So if we have a structure that looks like if P, then Q, P then we can conclude, therefore, Q. That's called modus ponens. If the argument is P, if P, then Q, not Q, therefore not P, this is called modus tollens. If we say the argument is P, therefore P or Q, we call this addition. That's going to be, all of these are going to be valid rules. If we know that P and Q is true, we know that P is true. If we know that P and Q are true, P and Q are true. This is called conjunction. If we know that if P, then Q, if Q, then R, then we can conclude if P, then R. This is called hypothetical syllogism, sometimes transitive rule. And if we say P or Q is true, not P, therefore Q, this is called disjunctive syllogism. And this was actually what we did in that first argument, because we said the error was either in module 17 or 18. It wasn't, or 81, I guess. It wasn't in 81, therefore it had to be in 17. So this is the form of that argument. Now what we're going to do is we're going to prove several of these. Let's begin by proving modus ponens. So we're going to be proving that this is valid. So we say P, if P, then Q, and P. So we're going to build a truth table with those components in it, and we're going to assume that the things above the line are true. That means we're going to mark off in the truth table everywhere where they are false and see if we're forced to conclude that Q is true. So here is our truth table, and we mark off every place where this one is false, and we also mark off with the red marks everywhere where this one is false, and we see the only one we're left is this one, and that says Q has to be true. So we observe that whenever this and this are true, the conclusion Q must also follow. Now, on simple things, sometimes you can have an easier solution. We can avoid writing the truth table sometimes by directly verifying that whenever the hypotheses are true, the conclusion is also true. So suppose that if P, then Q, and P are true, then we know Q has to be true, for otherwise it would have been false. Therefore, the argument is valid. This is a little bit more sophisticated, and brute force will always work, and sometimes nothing else will work. Let's do another one. Let's do this one. P, therefore, P or Q. So we make the truth table, and we cross out everywhere where P is false. So we cross out everywhere P is false, and we're forced to conclude that P or Q is true. That shows that whenever P is true, and P or Q is true, so that makes it a valid argument. Similarly, P and Q and P, there's our truth table. We cross out places where P and Q is false. We cross those out, and we're forced to conclude that P is true. Therefore, simplification is a valid argument. Now, this one is more involved. If P, then Q. If Q, then R. Well, what we do is we build the truth table. Now, notice here we have P, Q, and R. That means we have two states of nature here, two states of nature here, and two states of nature here. That is 2 times 2 times 2, or 8. So the truth table has to have 8 rows in this case. So we have 4 trues, 4 falses, pairwise 2 trues, 2 false, 2 trues, 2 false, and alternating true and false. That gives us all the possibilities. And we compute the truth tables for if P then Q, if Q then R, and P implies R. And we're going to cross out everywhere where the things above the line are false. So I cross them out here, and you can see that if we do that, and I've done it here in red, we say that the only thing that's left is we are forced to conclude that if P, then R is true in the remaining things. So therefore, hypothetical syllogism is a valid argument. This was the disjunctive syllogism, P or Q, not P, therefore Q. We build this truth table. We cross out everywhere where P or Q is false, or where not P is false. And we see that we're forced to conclude that Q is true. Therefore, disjunctive syllogism is a valid argument. Now, here are some problems from your book, and I'm going to ask you to do problem 7 and problem 8. So you know what to do, and we'll see how you did when we return for the rest of this video.